So to do the first principles derivation of ln, which is the natural logarithm, or log base e, I'm going to need to do some pretty fancy math magics in order to do some change of variables and take advantage of log laws in order to try and get some cancellation of these terms. So the first thing I'm going to pull, like the first dirty trick, is I'm going to take the fact that x plus h is the same as x times 1 plus h divided by x. Well, that's the first trick I'm going to pull. And if you want to double check it, x times 1 would be x, and x times h over x leaves me with just h. So the reason I'm doing that is I can replace this x plus h in my natural logarithm with this thing. And then what I'll have is a product of two objects inside a logarithm, which will allow me to use one of the log laws to split it into two pieces. So I'm going to do that first and see what happens. So my derivative will be the limit as h goes to 0 of ln of this fancy thing minus ln x. Now, the logarithm rule that I'm going to take advantage of is that the ln of two things multiplying each other is the same as the ln of those things done separately and then added. So what I'm going to be able to write here then is ln of this plus ln of that. And if you can see where that's going, it's going to end up isolating a ln x, which will cancel this one out. So dm by dx is the limit h going to 0 of ln x plus the ln of 1 plus h over x minus ln x over h. So if you can see, I have a ln x here, subtract a ln x, so those two things undo each other, and I'm left with my derivative is the limit of h going to 0 of ln 1 plus h over x over h. So here's where my next little bit of algebra acrobatics comes in. I'm going to make a tiny change to this structure here. I'm going to change my variables. And what I'm going to do is I'm going to introduce a new letter, p. And I'm going to replace h over x with this p. Now what that's going to accomplish is it's going to get the letter, right, this x, which has nothing to do with h. It's going to pull it out of my function. So if I do this, equivalently, if I bring the x up, then xp is the same as h. So if I make those changes, if h is going to 0, this is going away, then so is this. So now I've got the limit of p going to 0. The ln, this is too big, it's in my way, of 1 plus p over, I can replace h with xp. So similar to the sine and cosine examples, I have this x sitting here, and it's not affected by p going to 0. So I'm going to write it out in front. And it's in the denominator, so that's 1 over x sitting out there. And I have the limit of p going to 0 of ln 1 plus p over p left inside there. So just like the sines and cosines, I have a limit there that I'm not going to be able to evaluate like with algebra. I can't break it down, so I'm going to have to do it manually. So I'm going to pick a series of numbers that are getting closer to 0. I'm going to try p equals 0.001. So in it goes, it will be ln of 0.001 plus 1. Sorry, I got that backwards. 1 plus 0.001 is just 1.001 over 0.001. Now if I put that in a calculator, the ln of 1.001 is something tiny, divided by 0.001 equals 0.995. 9995. Okay, so I'm going to try and get closer. I'm going to do p is 0.1234 zeros and a 1. So if I fill that in, I'll be doing ln of 1 point, because it's 1 plus this, 1.1234 ones, all over 0.1234 ones. Put that in there. Ln of 1.1234 zeros and a 1 equals something really tiny divided by 0.1234 zeros and a 1. 0.999995. So 2 more zeros made 2 more 9s. It looks to me like these things are coming up to 1. So I'm just going to try one more to confirm the pattern. 0.123456 zeros and a 1. If I put that in there, ln of 1.123456 zeros and a 1 divided by 0.123456 zeros and a 1 gives me 0.9999995. So it looks to me that as p goes to 0, this thing, ln of 1 plus p over p, is going to 1. So this whole limit here is worth 1, and that's all. So in the next line here, I've got that my derivative is equal to 1 over x times this limit, which I just found out was only worth 1. And 1 times 1 over x is just 1 over x. So, in summary, by making this little manipulation, I was able to use log laws to split this into 2 pieces, which managed to cancel out the back piece and left me with this. This trick of unit conversion, going from h over x to p, let me get the x out of that logarithm and push it to the front. And then I evaluated this limit manually to find out it was worth 1, so that the derivative of ln x is 1 over x. So I'm just going to erase these, this p goes to 0 stuff with the cloth, which I seem to have lost. I'm just going to erase this, and then we're going to go and we're going to replace the ln with a generic log. So instead of writing ln, I'm going to write log. Okay, so what am I going to do? Let's do that with yellow. Okay, so if your thing was log base a, well then this would be log base a. This would be log a. This would be log a. This would be log a. These would all become log a's. Log a, A, log A. And this is the line where it changes. So at this point, I'm going to have to evaluate the limit of p going to 0 of log base A 1 plus p over p. And this is a hard thing to do because this thing is going to have a different value depending on what your base is. So you'd have to do it for log 5, and then you'd have to do it again for log 6, and then again for log 8, and then again for log 9.4. You'd have to do this for every single number. So some clever individual somewhere has sat down and figured out that this thing ends up being equal to 1 divided by the natural logarithm of whatever the base is. So when I got to this step here, when I found out that this limit was equal to 1, if I'm using a generic log instead of the natural logarithm, this limit ends up being worth 1 over ln A. So my final derivative then ends up being 1 over x ln of A. Now this is a bit weak, I'm just dropping that in there. But trying to prove that is going to be too difficult for what we're after. So if you're trying to show the derivative of a generic logarithm by first principles, at some point you're going to have to evaluate this limit, and you're just going to state that that's what it's worth, and it depends on what the value of A is. Okay, put that in there and you get this as your final derivative.